Paper title is Comprehensive Analysis of Sinkhole Attack or Rifle in Static, Mobile and Hybrid Network Environment. And I am the presenter. My name is Faisal Ali Garba. I have MSc and PhD in view. This is the outline of the presentation. We have abstract, introduction, literature review, methodology, result and discussion, conclusion, and future work. Abstract. The routing protocol for low-power and low-C networks RPL is extensively utilized in Internet of Things (IoT) environment due to its efficiency in managing constrained devices. However, it is especially prone to sinkhole attacks when rogue nodes post bogus routing metrics, contributing to large interruptions in network performance. These attacks degrade packet delivery, introduce delays, and drain energy, especially in dynamic networks. While several studies have explored the repercussions of sinkhole attacks in static networks, little emphasis has been devoted to how these attacks influence mobile and hybrid network environment, where node movement and diverse topologies offer extra obstacles. Understanding the comparative repercussions of sinkhole attacks in different contexts is crucial for building appropriate security tactics. This study gives a detailed simulation-based analysis utilizing Contiki 3.0 and the Kuja simulator to analyze the impact of sinkhole attacks on static, mobile, and hybrid networks. Simulations were done with varied network densities, 10, 20, and 30 nodes, and different percentages of malicious node, 10%, 20%, and 30%. Performance parameters such as packet delivery ratio, PDR, average end-to-end delay, overhead packet, energy consumption, and throughput were measured across all circumstances. The result revealed that mobile networks are the most vulnerable to sinkhole attacks, with considerable losses in PDR and increases in energy usage and delay. Static networks offer more stable performance, but are prone to long-term degradation when malicious nodes remain established. Hybrid networks demonstrate various consequences, with static attackers generating limited damage and mobile attackers spreading disturbance across the network. This result underlines the necessity for individualized security solutions based on the unique network environment. Static network demand rapid detection and isolation procedures, whereas mobile and hybrid networks benefit from dynamic, adaptive security solutions. Introduction. The routing protocol for low-power and low-C networks RPL is a crucial routing protocol created by the Internet Engineering Task Force (ITF) to address the unique challenges presented by low-power and low-C networks typically seen in Internet of Things IoT environment. Low-power and low-C networks comprise devices that perform under stringent resource limitations, such as restricted power, memory, and processing capabilities, frequently in circumstances characterized by unreliable network connections and minimal bandwidth. RPL creates a destination-oriented directly acyclic graph (DODAG) to optimize data routing within low-power and low-C networks. The protocol accommodates three principal traffic patterns: multi-point to point, wherein sensor node transmit data to a central node, point to multi-point, in which control information is disseminated from a central controller to multiple nodes, and point-to-point, facilitating communication between individual nodes within the network. This versatility enables RPL to provide a varied array of IoT applications, including smart cities, environmental monitoring, and healthcare systems. Problem statement. The sinkhole attack is a severe security vulnerability in routing protocol for low-power and low-C networks RPL that exploit the inherent vulnerabilities of the protocol. In a sinkhole attack, a malicious node provides falsified favorable routing metrics such as low power rank value to attract other nodes to route their packet through it. The rank value, which displays a node distance from destination-oriented acyclic graph (DODAG route), plays a significant role in discovering the optimal routing path in RPL. By falsely reporting a lower rank, the malicious node convinces surrounding node that it provides a better path to a target than other nodes in the network. The sinkhole attack not only impairs the integrity and availability of data, but it also makes it harder for the network to recover from such disruptions. The rogue node remain embedded within the network routing structure, making discovery and cleanup incredibly complex. This vulnerability underlines the importance for thorough security processes to detect and mitigate sinkhole attacks in RPL-based networks. Literature review. Overview of RPL and its vulnerabilities. The routing protocol for low-power IoT network RPL established by the Internet Engineering Task Force to suit the demand for Internet of Teams IoT environment. This environment is usually characterized by constrained devices with limited processing power, memory, and energy, which require particular protocols for efficient communication. Ripple is specifically designed to operate low power and loss network, which are networks prone to significant packet loss, variable connection quality, and restricted capacity. Ripple structures the network into destination-oriented directly acyclic graph where data flows along a route established by the data route. Okay, so we have already covered this, so let me just move forward. Sinkhole attack mechanism. The sinkhole attack is a severe security risk in routing protocol for low power loss network. Ripple due to its potential to fool genuine nodes into routing data through a compromised malicious node by displaying falsified good routing metrics. This technique exploits the rank structure of Ripple, which necessitates that node select a parent node with a lower rank to optimize the routing path to the root. In a sinkhole attack, the malicious node deceptively promotes an advantageous rank value, making it appear like an ideal parent to its adjacent nodes. Once the rogue node becomes a prepared parent, it has influence over a large amount of the network's traffic. At this step, it then drops the packet, similar to a black hole attack, thereby lowering the network's throughput. This propensity translate to greater packet loss, reduced packet delivery, and higher energy consumption as the node attempt to recover by continually routing data or initiating new route discoveries. Literature review. Related works. In a research by reference 6, the authors conducted analysis of sinkhole attack influence on network performance. They concluded that the malicious node manipulates its rank to deceive other nodes, tricking them into routing traffic through it. And once in control of the traffic, the rogue node selectively forward or drop packet. Their findings indicated notable drop in packet delivery ratio, increased latency, and heightened energy use. Reference 7 did a detailed investigation on the effect of sinkhole attacks across diverse IoT settings. The authors introduced the UOS IoTSH 2024 dataset, which focused on Ripple-based IoT networks under diverse attack circumstances. Their simulation demonstrated a sinkhole attack significantly impair network performance and PDR, particularly in instances involving dual attackers. Reference 7 further stressed the importance for effective detection system capable of reducing the attack's ramification across both static and mobile networks. Reference 8 have contributed greatly by presenting an experimental study of numerous Ripple-based attacks, including sinkhole attack. The investigation indicated that sinkhole attack could lead to serious network instability, especially in mobile circumstances where frequent topology changes excavate the attack's impact. The investigation found that the attack not only raises the quantity of controlled messages, but also increased energy consumption owing to frequent route reface. Gap in the digital literature. Although substantial research has been conducted on the sinkhole attacks routing protocol for low power LS network, several crucial gaps exist, particularly regarding the comparative evaluation of this attack across varied network environment, static, mobile, and hybrid. Firstly, most previous research largely focused on static network situations where nodes remain fixed. For instance, reference 6 evaluated the impact of sinkhole attacks on static networks, demonstrating notable loss in packet delivery ratio and increased management burden. However, their research does not extend to mobile or hybrid networks where frequent topology changes could magnify the consequences of such attacks. The dynamics of mobile networks where not optimum move could lead to varying effects on the performance measures like energy consumption, average end-to-end delay. Yet these features are not widely investigated. Contribution of this research. This study seeks to address the large gaps observed in the previous studies by giving a thorough comparative analysis of sinkhole attacks impact on routing protocol for low power LS networks ripple across static, mobile, and hybrid network scenarios. Unlike previous studies that have largely focused on static networks or provided limited insight into mobile and hybrid networks, the research investigates how sinkhole attack affect performance metrics such as packet delivery ratio, average end-to-end delay, overhead packet, energy consumption, and throughput across all the three environments. All right. So we'll move into the methodology. Methodology, we have the simulation environment. This study leveraged Contiki 3.0 operating system and its integrated network simulator Kuja to simulate the sinkhole attack in Ripple-based IoT networks. Kuja permits for the emulation of network environment with variable node configuration and attack scenarios, offering a full platform for analyzing the behavior of both static and dynamic network under different conditions. So we can see the simulation environment in this particular table. We have simulation parameters and then the value. Operating system, Contiki, simulator Kuja, network protocol, Ripple, and mode, Sky mode, and MAC layer protocol, CSMA, radio duty cycle, Contiki MAC, transmission 50 meters, interference 100 meters, traffic type UDP, simulation duration 10 minutes. node density 1020 and 30 nodes, mobility model, random waypoint for mobile and hybrid networks. Then simulation seed is random seed, and routing metric is ATX. Now, network parameters, network is supposed to accommodate 1020 and 30 nodes under the above conditions. For mobile and hybrid networks, the random waypoint mobility model is utilized to ensure that nodes move dynamically across the network space. Node density is adjusted to examine its impact on network performance measures. Each simulation runs for the duration of 10 minutes, and which is sufficient to observe the long-term repercussion of sinkhole attacks. So we have the result and discussion. Simulation result for 10 nodes. We have is presented in this table too. We can see the values for the PDR, for the average end-to-end delay, for the overhead packet, for the energy consumption, and then for the throughput. And then we have the graph simulation result for 10 nodes in static network. So it goes on for the simulation result for 20 nodes is represented in table 3, and the graph is presented in figure 2. And then we have simulation result for 30 nodes in static network in table 4, and then we have the graph in figure 3. And then we have table 5, simulation result for 10 nodes in mobile network, and also we have the graph presented in figure 4. And then we have table 6. Table 6, simulation result for 20 nodes in mobile network is presented in table 6, and then we have the graph showing simulation result for 20 nodes in mobile network. And then we have figure 7, simulation result for 30 nodes in mobile network, and then we have the graph in figure 6. So we have figure 6. All right, so this is a repetition. So we have table 8, simulation result for 30 nodes in hybrid network, static attackers, and then we have the graph in figure 7. Then we have table 9, simulation result for 20 nodes in hybrid network static attackers. And then we have the graph showing result for 20 nodes in hybrid network static attackers. So it goes on, the tables go on up to the last table. So let's move to the discussion. We have the hybrid network model incorporate both static and mobile node, provide a unique context to analyze the impact of sinkhole attacks. With static attackers, PDR is severely affected, dropping from 12.68 in reference simulation, and in 30 node simulation, PDR demonstrates. So we have the conclusion and the discussion. Everything result in the result and discussion is presented here. And then we have the conclusion. The study presents a full evaluation of the impact of sinkhole attack across the 3 diverse network environments, static, mobile, and hybrid. The research has shown that static networks are less susceptible to frequent interruption, but suffer from persistent attacks when malicious nodes are deeply embedded in the network. In contrast, mobile network demonstrate the most dramatic performance deterioration with drastic reduction in packet delivery ratio and increased energy consumption due to the frequent requirement for route interface. So we have future work, and then we have the references are the references. Thank you very much for listening to this presentation.